Okay, I don't know how to wish you because you may watch this in the morning session, afternoon, evening. I can't really say good morning, good afternoon, good evening. Okay. Anyway, good day, good night. Anyway, that's nice. I hope we will meet very soon and then continue our discussion to seeing each other physically. I shall continue the discussion of Hartnell governor and I have written the title what I intend to discuss. Analysis of Hartnell governor when R equal to R2 and R2 is less than R mean. Sorry. I shall quickly revise what all terms I have used. Okay, mass of each ball as MB, mass of sleeve as MS, then A is the length of the bell crank lever, which is a sleeve arm bell crank lever. Then B, the length of the ball arm of the sleeve bell crank lever. And C is the distance between the fulcrum and the axis of rotation of the spindle. And then K is what is the stiffness. Then I also have what's called as in level R. I call it as refer it as the radius of rotation of the balls. And I have been using R minimum, that is the corresponding to the lowest position of the sleeve. Then what is the radius of rotation of the balls? R minimum, R mean. R mean is a term which I have used. It is not a standard one. What is that R mean? Radius of rotation of the balls when the ball arm is vertical or ball arm is parallel to the axis of rotation of the spindle. Okay, that's what I have called it as R mean. And R1 and R2 are any two positions in between minimum and the maximum position of the sleeves. Then I also have what is called as R max. Then accordingly the speeds omega minimum, omega 1, omega 2, omega mean, like that I have different speeds. Okay, so now let me come back to this analysis of Hartnell governor when R is equal to R2. Okay, let me draw the sketch. Quite simple. Okay, I am drawing only the diagram which is relevant for the analysis purpose. This is the axis of the spindle. Then immediate next thing what I mark is what is called as the fulcrum position. This is the fulcrum position, and as per my notation, this distance I have called it as a C. C is the distance between the fulcrum of the bell crank lever and the axis. Okay, so now the radius of rotation R2 is less than R mean. That means the ball arm is something like this. This is the ball arm, and I have represented the position of the ball, and this is what is R2. This is R2, and this is the ball arm, and its distance is B, and perpendicular to this, because the two arms of the bell crank lever, they are perpendicular to each other. Let me assume that this is the sleeve arm. Okay, and this distance is what is A. Okay, so now I just before I represent the forces etc., I just compare. Okay, I draw this horizontal line and also vertical line. So this is what I mean by the mean position. Say this is what I call it as the R mean. Okay, at the mean position, the sleeve arm is like this. Now, for the analysis, this is the position, and therefore I shall show and call this distance as the displacement of the sleeve from the mean position to position 2. This is what I have called it as X2 mean, the displacement of the sleeve between mean position and second position. This I shall call it. Okay, so now I shall urge the speed. Now the speed of the governor or the speed of rotation of the balls. Okay, so this is what I shall call it as omega 2 radians per second. omega 2 radians per second. And let me indicate the forces. Okay, the centrifugal force, this is nothing but mb into omega 2 square multiplied by r2. Okay, and the weight of the ball, this is mb into g, that will be acting like this. And at the roller, so I have whatever the central force, this is the sleeve here, this is the sleeve, the weight of the sleeve is acting in the downward direction, also the spring force. So that I shall write it as ns into g plus s2 divided by 2. So this is the y divided by 2 because I am taking only one half, that's why I am taking half. Exactly the same amount of force you have on the other side also. Okay, now, so I just wish to write how much is this distance. This is nothing but r mean minus r, this distance. Okay, so let me write down this distance because this is the perpendicular distance between this force and this fulcrum. This I shall call it as B2. And similarly, I just extend it, draw a line, and this distance I shall call it as A2. Why? Because this is the perpendicular distance between this force and the fulcrum. This force multiplied by this A2 will give you what is the moment. Okay, so now I have three forces. Let me calculate this moment about this point is in anti-clockwise direction. The moment due to the weight of the ball is also in the anti-clockwise direction, and the moment due to this centrifugal force is in the clockwise direction. So in the clockwise direction I have only one moment, and in the anti-clockwise direction I have two moments. It was exactly different in the earlier case when this ball is with this arm is on this side. That time I had two clockwise moments and only one anti-clockwise moment. Now I have two anti-clockwise moments and one clockwise moment. Okay, so on the left hand side I shall write down the moment which is only one. That is nothing but the clockwise moment. That is nothing but mb into omega 2 square multiplied by r2. This multiplied by the perpendicular distance which is equal to b2. So this is a force multiplied by the moment r, b2. This is equal to, okay, mb into g, this is the force multiplied by the perpendicular distance between this force and the fulcrum. That is nothing but this distance, that is same as this, multiplied by r mean minus r2, plus the moment due to this, that is nothing but ms into g plus s2 divided by 2 multiplied by a2. So this is what is the equation, analysis equation. But I have two terms which are new to me, new to my discussion, like B2. I know MD, omega 2, R2, MD, G, R, mean, R2, so all S2, all these are familiar, but I don't know what is B2, what is A2. Okay, so I need to find out those values. And before I do that, okay, I shall make use of one more relationship here. Say, let me take this triangle for example. Okay, and this triangle. Both of them are similar to each other. This triangle and this triangle, they are similar to each other, and I shall make use of this x2 mean. What is the meaning of this? The displacement of the sleeve from the mean position to position 2. So this divided by a, this divided by a, this distance divided by this distance is equal to this distance divided by this distance. This is equal to R mean minus R2 divided by B. Therefore, I am able to find out what is called as x2 mean is equal to A upon B multiplied by R mean minus R2. Okay, so I haven't, you may have a surprise why I found out this. Anyway, I am going to relate now. Okay, now the next one I would like to write down what is S2. S2 I have here. S2, the spring force at this point, at this position, So do you agree that? So when the sleeve is at the mean position, I am referring the spring force as S mean. The spring force at the mean position is S mean. The spring force at this position is S2. Okay, compared to the mean position, the sleeve has come down. That means the spring which was in this position, which was how much it was compressed, but by the time it comes here, the compression has decreased. Therefore, what I can say that S2 is less than S mean. Okay, S2 is less than S mean. Therefore, S2 is equal to S mean minus how much? So how much expansion? That is nothing but K. K is the stiffness of the spring multiplied by x2 mean. This is the displacement. This is further. Okay. So it is like this. You have a spring, say, in the mean position. It is already compressed. This is what I mean. S mean. Okay. It is not. So this side, this is sleeve only, and this end is what is fixed. Okay, this end is fixed. This is the sleeve. The sleeve has come down. Sleeve has come down. The sleeve has come down means the spring has further expanded. Therefore, this S2 is less than S mean. So therefore, S2 is given by S mean minus K into X2 mean. This is how you can find out what is S2. Then I would like to find out what is A2. So A2 is this distance. That is nothing but this distance. That is nothing but square root of the square of this minus this. Applying the Python of this term. So A2 is equal to square root of A square minus X2 mean square. This is how we can find out what is the value of A2. And on the same lines, if I want B2, this distance, this is nothing but this square plus this square is equal to this square. Therefore, on that lines, B2 I can write down B2 is equal to B square minus X, not X. It is R mean minus R2 whole square. This is nothing but B2. So you can find out what is the value of B2 from this and substitute here and apply this, and you can easily find out the unknown. Okay, so this is the method. Please remember, I don't intend to derive any equation here and which you can use ready-made and to solve the problem. I am not sorry, I don't have such an expression in the case of Hartnell governor, because there are so many things. The analysis what I have shown here may slightly vary from the real problem. So what I have assumed, for example, okay, so I have assumed that the bell crank lever, say something like this, okay, this is the axis, and this is the sleeve arm, this is the ball arm, and this is what I have assumed as the fulcrum. Okay, so this position I am calling it as mean position, assuming that the minimum position, the ball arm will go something like this, and for the maximum position, the ball arm go like this. It will be, the ball arm will be moving from this position to this position, and this is what I am calling it as mean position. But in real problem, in a different problem, it may be something different. This mean position, what I am referring, that itself may be the minimum position. Okay, that itself may be minimum position, and in that case, this may be the maximum position. And therefore, depending upon the position of the sleeve, so So what is minimum, what is maximum, etc., that may change. Okay, I am referring the mean position. How? So the ball arm is vertical, or in other words, the ball arm B, the dimension B is parallel to the spindle axis. That's what. With respect to that, I would like to compare the other positions, and for that purpose I have used mean position. So mean position, there is nothing like the standard one what I have used, and I have used it for my analysis purpose. So one more very important thing, okay? One more important thing is, so this whatever I have shown here, and this is applicable for case 2 also, okay? So here I find out x2, this, etc. So by chance this R mean minus R2 is very small. R mean minus R2, okay? This value is very small. If that is very small, in that case, what happens? What will be the value of A2? You can see here A2 and B2. If R mean minus R2 is small, in that case X2 also is going to be small. X2 mean is here. If this is small, then this also is small. In that case A2 and B2. In this case, this is small and this also is small, and you have a square of a smaller value. If it is a small value and the square of that is still smaller, in that case A2 is square root of A square minus very small value. In that case A2 is almost equal to A. A2 is A, B2 is equal to B. In that case, so B2 becomes B and A2 becomes A, and this becomes 0, and therefore you have only this and this. So this, sometimes it is asked in the problem that you don't have to take the obliquity effect. So when the arms become oblique with respect to the vertical axis, if they become oblique, they make angle, then you don't have to take that into account while writing the moment equation. So in that case, the weight due to the moment due to the weight of the ball will never come into picture. So in that case, it is only the centrifugal force multiplied by B is equal to the force at the sleeve multiplied by A. Okay? This is what we mean by the obliquity effect. Maybe in one of the problems I shall show both. If I take obliquity effect, how the analysis is going to be, and if I don't take obliquity effect, then what will be the change, that I shall show you in one of the problems. Okay, now let me take one problem. I wish you already have that problem written it, and I want you to read along with me loudly. And while reading itself, we shall try to understand the problem and also start copying the data, what is given in the problem. This is a problem from February 2006, and this is for 10 marks. It goes like this, quite simple. A Hartnell governor moves between 300 rpm and 320 rpm for a sleeve lift of 20 mm. Okay, so a Hartnell governor, and 300 rpm is the lowest speed and 320 rpm is the highest speed. And for this, the sleeve undergoes a displacement of 20 mm. Okay, let me write down what is this, what are these things. 300 rpm, what is 300 rpm? 300 rpm, what is this? This is nothing but N minimum. It is very clearly said that the governor runs between 300 rpm and 320 rpm. Therefore, 300 rpm is the lowest speed. And from this, I wish you to find out what is omega minimum, so many radians per second. And you also know what is N max, that is 320 rpm. So find out what is omega max, so many radians per second, and 20 mm 20 mm. What is this? 20 mm. Go back to the notations. What I have used x minimum to x max. X is the notation I have used for sleeve displacement. Okay, for this 20 mm, it is between minimum position and maximum position. That is 20 mm. And this I would like to convert it into meters. 20 into 10 raised to minus 3 meters. Okay, the next information. The sleeve arms and ball arms are 80 mm and 120 mm respectively. So sleeve arm we are referring it by a, small a, 80 mm. So again 80 multiplied by 10 raised to minus 3 meters. And ball arm, if you are very careful and very cautious and if you are confident, quite confident, I don't mind you to continue these values in millimeter, but I don't wish you to make any kind of mistake. Therefore I shall take all lengths in terms of meters. And once you practice and you are very sure, and if this is making you uncomfortable, then you can continue in millimeter, centimeter, whatever units, but you have to be very, very careful. So B, the ball arm is 120 mm and 120 into 10 raised to minus 3 meters. Okay. The next sentence, the bell crank levers are pivoted at 120 mm from the governor axis. This is nothing but C. C is 120 mm. C is 120 into 10 raised to minus 3 meter. Full stop. The weight of each ball is 25 Newton. Okay. So the weight is given. MB multiplied by G is 25 Newton. But I require what is MB? The mass 25 divided by 9.81. Get this? This is so many kgs. Okay. Then next, the ball arms are parallel to the governor axis at the lowest equilibrium speed. Very, very important statement. The ball arms, what is that? Ball arms are indicated by B. Small b, no? The length. This B are parallel to the governor axis. Parallel to governor axis. So this is what we are calling this position. What is that? In our analysis we called it as the mean position. If the ball arms are parallel to the spindle axis, then we call that position as the mean position. But here what it says, the ball arms are parallel to the governor axis at the lowest equilibrium speed. Okay, so this is for minimum position. Okay, for minimum position itself, this is the ball arms are parallel to the governor axis. Determine the stiffness of the spring. What is asked in the problem is what is K? What is K? Okay, so now for this we shall draw a diagram. Okay, so the first one, the first analysis is for minimum position. Minimum position, that is nothing but the sleeve is at the bottom most position. Okay, quick. So I go the spindle axis. Then I shall show what is the fulcrum. And this distance is already given. This is what I call it as C. And C is known. And the minimum position, the ball arms are parallel to the governor axis. Therefore, this is the minimum position. And this dimension is what is B. And once this is drawn, then automatically you can draw the horizontal, that is sleeve arm. This is what is A. So I know A, I know B, I know C. Okay, everything is known. Then what will be the value of R? This is nothing but R minimum. Please remember, R minimum in this case will be equal to C. Because this is parallel to the spindle, this distance is same as this R minimum is equal to C in this case. Okay? Then let me show what are the forces. I have what is called as MB, which I have found out from there, I know. Then omega minimum square multiplied by R minimum. Please remember, I know MB. I know omega minimum is known. Then you also know R minimum. R minimum is same as C. Please remember, R minimum also substitute it in terms of meters. Okay. Then you have what is called as the weight mg into g. So that passes through the fulcrum. Therefore, there won't be any moment due to that. And then here, so one more information. Okay, if I go back and try to find out what is the mass of the sleeve. Okay, so I go through the problem once again and then I don't find any information about the mass of the sleeve, and therefore I shall assume that mass of the sleeve is not given and 0, and this is assumed. We are assuming it, the mass of the sleeve as 0, because we have no information in the problem. Okay, so even if you assume some value, then also absolutely no problem. Okay, so now I shall assume it as 0 for convenience. Okay, the mass of the sleeve is 0, then but there is spring force. What is the spring force corresponding to the position of the sleeve? What is the position of the sleeve? At the minimum position, and therefore the spring force I shall call it as S minimum. S minimum divided by 2. So MS is 0, 0 into G plus S minimum, whole thing divided by 2. Okay, now very simple. Then apply take the moments due to all the forces about the fulcrum. So I have the one moment due to this in the anti-clockwise direction and another moment in the clockwise direction. This moment due to MB into G is 0, therefore it is simple. S minimum divided by 2 multiplied by A is equal to MB omega minimum square into R minimum. Okay, so you know A, you know MB, you know omega minimum, you know R minimum. The only unknown is S minimum. Find it out. This will be so many newtons. S minimum is basically a force in the spring. So it will be in terms of Newton. This is what you are going to find out. I am not substituting and calculating, I am giving you the work of that. So I hope you will complete that. So you know now S minimum. So S minimum is known. Okay. Now I am trying to go to the maximum position, and then for that I shall rub the space. So I know S minimum now. So now the second maximum or maximum position or maximum position. Okay, again the spindle axis, then again the fulcrum of the bell crank lever. This distance remains same. This is C. Okay, so now, okay, where is the ball arm? So I know the mean position, that is minimum position, it was vertical. The speed has increased, and therefore the ball arm goes this side. Let me assume that this is the position of the ball arm and this is the ball, and this distance I shall call it as R max. This is R max. And perpendicular to the ball arm I shall draw what is called as the sleeve arm, which is also called as the roller arm. And this distance is what is B, and this distance is what is A. Okay, they are known to you now already. And so I just draw a vertical position corresponding to the minimum position and a horizontal line here corresponding to the minimum position. Okay, the sleeve has moved from minimum position to this maximum position, and I know how much is this distance. What is that? This distance is x minimum to maximum. That is already given. That is 20 mm. So I know this distance. Okay, let me show all the forces now. This is the centrifugal force MB. Okay, what is the speed now? The speed is omega max. Please remember, MB is known. Omega max square. This also is known. R max. R max I don't know. R max I don't know. Little later I shall show you how I can find it out. R max I don't know. Then I have what is called as the weight of this ball, MB into G. MB into G. Then at this, again the sleeve is not there. The sleeve is not having any weight, but the spring is there. The spring force corresponding to the maximum position of the sleeve, which I am calling it as S max. S max divided by 2. Okay, so I shall call this distance as A2 or A2, or let me call it as A2 or A1. Let me call it as A1. And let me call this distance. Well, how much is this distance? This is R max minus R minimum, because this is the position corresponding to the minimum, therefore this value is R minimum. This distance is R max minus R minimum. Okay, then how much is this distance? This distance I shall call it as B2. I shall call it as B2. Okay, so now let me make use of the similar triangle, this similar triangle and this similar triangle. From that I shall get x min max divided by this distance A is equal to this distance. What is this? That is R max minus R minimum divided by B. Okay, so in this what all things you know, please check that. X min max, the displacement of the sleeve between minimum and maximum 20 mm, that you know. So this is known. This is the length of the sleeve arm, this also is known. R max, this is unknown. And R minimum, which is same as C. R minimum is equal to C, this also is known. B is also known. And from this you find out what is R max, so many meters. This you find out. So R max is known now. Okay, so R max is known. Okay, then, so what is A1? A1. Okay, A1 is nothing but the square root of A square minus x min max square. So please do this, and this is what A1 is known to you. And on the same lines, you can also find out B1, which is nothing but B square minus R max minus R minimum whole square. This is what is your B1. Okay, so now I shall write down the moment equation. What is the moment equation? You have two moments which are in the clockwise direction, and you have one moment in the anti-clockwise direction. That is nothing but S max divided by 2 multiplied by A1 is equal to MB into G multiplied by R max minus R minimum. This multiplied by this plus MB into omega max square into R max, this is the force, multiplied by B2. Check what all things you know. S max is unknown. A1 is known, that I have found out. Then MB, G, R max, R minimum, all these things are known. MB is known, omega max is known, R max is known, B2 is known. All things are known, and from this, what do you find out? So you find out what is called as S max. S max you find out, this is so many newtons. Okay, you know S minimum, you know S maximum, okay, and you can easily find out what is called as the stiffness. So stiffness is equal to S max minus S minimum divided by what is the displacement of the spring between minimum and maximum. That is nothing but the X min max. If this is in Newton, this also is in Newton. If this is in meters, in that case you will get so many Newton per meter. If this is in Newton and this also is in Newton, and if you substitute this in millimeter, then you will get it so many Newton per millimeter. Okay, this is what is asked. You are asked to find out what is the stiffness of the spring. Okay, so this is how you can. So every problem has to be treated as if it is something new, and you have to apply the method what you have learned in the demonstration of the analysis and find out the unknown things. Okay, I hope you have understood. If you have any difficulty, any doubt, please ask me. Let me know. I shall be very happy to clarify it. Thank you. Good day.